So we have an infinite series again, infinite geometric series. First term is 90, second term is negative 30. We can again write down that pertinent information that we've always written down. Term 1 is 90. Common ratio I can pick off is 1/3 negative style here. It's an alternating series. That negative 1/3 is between -1 and 1. So that's like a little check we might want to do to make sure that that's a decaying series. If that's the case, we can figure out the sum of this series, the infinite sum, by plugging in 90 over 1 minus -1/3, which is 90 over, well, we need to find a common denominator, and we're adding 1/3. So 90 over 4/3. And if we invert and multiply, because we're dividing by a fraction, we get 270 over 4. And that happens to reduce to 135 over 2, which is a great number. So a pretty simple application of sum infinity, simply just using a formula T1 over 1 minus r. And we can do a couple of more questions like that, but instead let's move on to a little bit more interesting questions. How about expressing a continuous decimal, 0.65 repeating as a fraction? So what we have is 0.65 repeating. What we want to do is break that up into the specific decimal spots. So that's 0.6 plus 0.05 plus 0.005 plus, and that carries on forever. So right away what we see is we have basically an infinite series, 0.05 and on, which we can deal with in terms of a sum infinity. So we're going to deal with just that term. We're going to pretend that A is 0.05, just the repeating part. Let's write that as a fraction maybe. That's 5 over 100. We're going to deal with a common ratio. Common ratio here is 1/10. So let's figure out sum infinity for that series. Sum infinity is 5 1/100ths over 1 minus 1/10. 5 1/100ths. 1 minus 1/10 is 9/10. Again, we can invert and multiply. 5 1/100ths times 10/9, and we get a little bit of cancellation here, and we end up with 5 over 90. So the sum of the repeating decimal portion is 5 over 90. So when we want to build 0.65, we can write it as 0.6 plus 5/90ths. If we want to express this as a single fraction, though, 0.6 we need to rewrite as 6/10 plus 5/90ths, and find some common denominators. Probably a common denominator of 90, so let's multiply 6 by 9 to get 54/90ths plus 5/90ths, and we get 59/90ths. If you'd like, it's probably a good idea to maybe punch that in your calculator, make sure 59/90ths works out to be 0.65 repeating. Third example really illustrates the idea of us having a finite sum. So determine bounds on x so that the given infinite geometric series has a finite sum. As soon as I see this combination of infinite geometric series and finite sum, that tells me that we need to have our common ratio between -1 and 1. That's the tip-off here. So we need to force our common ratio to be between -1 and 1. Let's figure out what the common ratio is here. This series has some x's in it, that's fine. If we can't pick off a common ratio, what we do is we always take term 2 divided by term 1, or term 3 divided by term 2. So let's try that. Let's go term 2, which is x plus 1, and divide it by term 1, which happens to be 2. So we have the common ratio has to be between -1 and 1. We know the common ratio is x plus 1 over 2. So what we're going to do is we're going to wedge that between -1 and 1. Now, this is a little bit loose in terms of how we solve inequalities. We should really be breaking this up into multiple inequalities, but make sure that the one thing that you need to remember is if you multiply or divide by a negative number, you need to flip the inequality signs. In this case, we can solve for x by multiplying everything by 2. And subtracting 1. So what happens is we get an answer of when x is between -3 and +1, the geometric series that we have above will work out to be a decaying series, and that's what we want for it to have a finite sum. If the x values are outside of the -3 to 1 range, what we end up would be a growth series and an infinite sum, or a sum that did not exist. Finally, this ball dropping. A ball is dropped from a height of 4 meters. On successive bounces, the ball rises to 60% of its previous height. Determine the total vertical distance the ball travels before coming to rest. I like the idea of drawing just a little bit of a bouncing ball kind of idea, just to get an idea of what's going on. Originally, the ball is dropped from 4 meters. So we start 4 meters high, and it drops that distance. So the first term here is 4 meters. The common ratio here is 60%, so 0.6. Determine the total vertical distance. So total vertical distance the ball travels before coming to rest. So we don't have a specific end term here. We're not saying, okay, after 6 bounces or 10 bounces, I want it to come to rest. So for me, that means a sum infinity idea. Let's roll this through the formula. We get sum infinity equals 4 over 1 minus 0.6, which is 4 over 0.4, which is 10. And don't forget units, which is 10 meters. Now there's a bit of a problem with this. If we just did sum infinity with 4 and 0.6, the only vertical distances we're counting is the drop distance. So in fact, what we need to do is we need to take that distance, which equals 10 meters, and multiply it by 2. So we get 20 meters because we want it both the up direction and the down direction. Again, there's still a little bit of a problem with this, is that we don't have the original 4 meters thrown up. So what we need to do is we need to subtract off the original height, because I don't want to double count that. And we get a final answer of 16 meters. So to recap, it's a sum infinity question. We double that because it heads both up and down that amount, except we need to subtract off 4 meters, which is the original amount. It didn't go up. This ends the examples for sequences and series infinite geometric series.